Pluto, a far-off and tangling world, was, for a time, a solitary and fair planet person from our planetary family. Regardless of upsetting clarifications by leading astrophysicists Neil deGrasse Tyson and Michio Kaku, Pluto was brought back into the spotlight with astounding responsiveness. They suggested that this cold world is on a potentially stacked depiction with Neptune. Yet how could this work out? Moreover, what might be the aftereffects of such a significant event? Are we witnessing a dazzling, affected bizarreness? Or is there something more to this approaching perpetual mishap? Come with us as we review the potential consequences of a Pluto-Neptune influence. Pluto, a former planet that was reclassified to a more modest individual planet, remains a subject of interest and focus in the vast community. As indicated by steady figures by leading experts, Pluto's course is dangerously close to Neptune's. Leading astrophysicists Neil deGrasse Tyson and Michio Kaku are both raising the alarm about a potentially hazardous disaster between these two celestial bodies that could pose a significant threat to Earth. But how is such an event even possible? Pluto's orbit around the Sun is unlike any other planet in our closed planetary system. It requires a stunning 248 years to complete a single orbit. This means that since its discovery in 1930, it hasn't even completed one full trip. Yet the intrigue doesn't stop there. Pluto's path is characterized by its highly distorted shape, deviating significantly from the nearly circular orbits of the larger planets. What makes Pluto's orbit even more perplexing is its inclination, determined to be at 17 degrees to the ecliptic plane. This highly unusual path, compared to other planets, adds layers of complexity to its orbital model. Perhaps one of the most captivating aspects of Pluto's orbit is its resonance with Neptune's. For about 20 years in each orbit, Pluto actually draws closer to the Sun than Neptune, defying expectations based on their positions in the planetary assembly. This prompts the natural question: why hasn't Pluto collided with Neptune? The answer lies in the gravitational effects of various planets. The evaluation of Pluto's orbit began shortly after its discovery. Initially, astronomers struggled to make sense of its unusual path. Unlike other planets whose orbits lie relatively close to the ecliptic plane, Pluto's orbit stood out with its steep inclination and erratic shape. The mystery associated with the confirmation that Pluto's orbit does indeed cross Neptune's is the stability of Pluto's orbit amidst these complexities. This is evidence of the intricacies of celestial mechanics. The three-body problem in space involves understanding how three objects, like Pluto, Neptune, and the Sun, move and affect each other with their gravity. It's like trying to predict their future positions based on where they start and how they pull on each other. In Pluto's case, this problem demonstrates how its orbit, Neptune's orbit, and the Sun's gravity all interact in a complex manner. Terms like asymptotic libration, scope libration, and VZK wobbling are part of this puzzle. According to astrophysicists, what keeps all planets in their orbits is a kind of libration. In the case of Pluto and Neptune, this term implies that whenever Pluto crosses Neptune's orbit, its position is consistently at least 90 degrees away from Neptune. This spatial separation is crucial in preventing their orbits from influencing each other. Scope libration, on the other hand, refers to the up and down movement of a celestial body in its orbit. For Pluto, this means that when it comes closest to Neptune or any other giant planet, it is positioned far above their orbital plane, contributing an additional layer of safety from potential collisions. Another significant factor in this scenario is the VZK wobbling, named after three researchers, V. A. Appel, L. V. Kuznetsov, and K. U. Du, who studied the motion of celestial bodies. This wobbling describes how three space objects, like Pluto, Neptune, and the Sun, exert gravitational pulls on each other, affecting their movements. For Pluto, the VZK wobbling helps explain why its path near the Sun is so unusual. Despite its apparent instability, this wobbling plays a role in keeping Pluto's orbit stable for an extraordinarily long time. These factors collectively help maintain Pluto's orbit, ensuring it doesn't collide with Neptune or deviate dangerously. The three-body problem highlights how the orbits of celestial objects change due to gravitational interactions. Studying this helps us better understand Pluto, our neighboring planetary system, and distant stars and planets. Mathematical simulations in the late 1980s revealed that, despite these stabilizing properties, Pluto's orbit is chaotic, with minor deviations in initial conditions leading to significant differences over time. However, these odd properties of Pluto's orbit have been found to maintain consistency over very long periods. Later computer simulations have helped us understand how the giant planets, like Neptune, Jupiter, and Saturn, affect Pluto's orbit around the Sun. Neptune has a unique relationship with Pluto, where for every 2 orbits Pluto completes around the Sun, Neptune completes 3. This resonance helps keep Pluto's orbit stable. However, Neptune isn't the only factor. Jupiter's gravity also plays a crucial role in protecting Pluto's orbit, with Saturn contributing as well. These simulations show that Jupiter's gravity alone is strong enough to ensure Pluto remains on a stable path for billions of years. Together, Neptune, Jupiter, and Saturn appear to collaborate to ensure Pluto can continue its journey through space without major disruptions. These peculiarities are vital in the broader context of the universe for maintaining the order and stability of celestial bodies. Without these factors, the solar system as we know it would be a place of much greater chaos and instability. Bodies like Pluto could collide with others or be ejected from their stable orbits, triggering a cascading effect on other celestial bodies. For Pluto, particularly with discussions about its potential collision with Neptune, understanding its orbit is critical. This gives us a clearer picture of the dynamic nature of the solar system. Pluto's example demonstrates how even the most unstable orbits can achieve harmony through the intricate interplay of gravitational forces and orbital mechanics. It also underscores the importance of continuous research and analysis to better understand our place in the universe. Exploring the depths of space often leads us to confront the whimsical nature of celestial bodies, and Pluto's orbit is a perfect example of this unpredictability. The concept of orbital resonance, which suggests the delicate dependence of a celestial body's orbit on its initial conditions, is clearly illustrated in Pluto's case. This means that even slight variations in the dwarf planet's position or speed can significantly alter its long-term orbit. Using computational simulations has been immensely valuable for understanding how Pluto moves in space. These simulations employ complex mathematics to model how Pluto, along with other celestial objects like Neptune, influences one another through gravitational interactions. By tweaking small details in these simulations, astronomers can observe how even minute changes can have a significant impact on where Pluto ends up over time. In the late 1980s, these simulations revealed something truly fascinating about Pluto's orbit. Despite having mechanisms like asymptotic libration and scope libration to keep it stable, its orbit can still be incredibly erratic. If even a microscopic difference exists in Pluto's starting position or velocity, its trajectory could look entirely different over thousands or millions of years. Yet, despite this apparent chaos, Pluto's orbit remains stable for billions of years. This suggests that Pluto's journey around the Sun has an underlying order, even though it might appear chaotic at first glance. This phenomenon is particularly important when studying chaotic orbits like Pluto's, as it presents enormous challenges. The inherent nature of such systems means that long-term predictions are often fraught with uncertainties. While mathematical simulations provide an incredible resource for understanding and predicting the future behavior of celestial bodies, they also highlight the limitations of our models. These simulations rely heavily on the accuracy of initial conditions and the complexity of the interactions they mimic. Any slight error or deviation can drastically alter outcomes, making precise predictions a daunting task. Moreover, the chaotic nature of large orbits like Pluto's serves as a reminder of the ever-changing and dynamic nature of the universe. While we have made significant strides in understanding space, Pluto's example reminds us of the limitations of our knowledge. Understanding the gravitational effects of the giant planets on Pluto's orbit offers critical insights into the broader dynamics of the solar system. It shows how the presence and positioning of each planet can have far-reaching implications for the stability and trajectory of other celestial bodies within the system. So why are notable astrophysicists suddenly raising concerns about a potential collision between Pluto and Neptune? Despite all these complex forces working to prevent such an event, Neil deGrasse Tyson, a renowned astrophysicist, offers a thought-provoking perspective. Known for his role in reclassifying Pluto from a planet to a dwarf planet, Tyson provides a detailed analysis of the evolving nature of celestial mechanics and the public's fascination with the lesser-known corners of space. Pluto's reclassification is framed within the ever-expanding understanding of our solar system. Tyson views the reclassification not as a diminishment but as a necessary adjustment to reflect our growing knowledge of the many bodies surrounding our Sun. His approach to celestial mechanics is one of continuous learning and adaptation. He recognizes the complexities of Pluto's orbit and its interactions with Neptune as part of the intricate dance of the cosmos. While Pluto's orbit is stable for now, Tyson suggests that it could undergo significant changes in the future. This possibility serves as a reminder of how much we still have to learn about the forces shaping our solar system. The example of Pluto demonstrates that even the most seemingly erratic orbits can achieve a state of harmony through the complex interplay of gravitational forces and orbital mechanics. As we continue to explore the depths of space, we are often reminded of the unpredictable nature of celestial bodies. Pluto's orbit, with its peculiarities and resonance with Neptune, serves as a perfect illustration of this unpredictability. It highlights the importance of ongoing research and exploration to deepen our understanding of the universe and our place within it.